if you have two objects, which one has a higher temperature than the other one, and put those two objects together, some heat is going to be transferred from the hot one to the cold one. And basically you can transform some of that heat using some methods like heat engines to mechanical work. The question is, what's the maximum amount of work you can get out of a system like this? Two objects, 1 and 2, with heat capacities of C1 and C2. The first one has a temperature of T1, the second one has a temperature of T2, and T1 is greater than T2. Basically, to answer this question, we have to use a heat engine between these two heat reservoirs, which has the highest efficiency. And we all know that that engine is the Carnot engine. So let's say we have a Carnot engine getting some heat, this one giving some heat to the other one and giving us some work. So what I'm going to do is that I would put a Carnot engine between these two objects, let the cycle run one time. Some heat dq1 is going to be transferred from our first object to the Carnot engine. Some heat dq2 is going to be transferred from the Carnot engine, the second object, and some amount of work is going to get out of the system. And the temperatures T1 and T2 are going to change a little bit. Then I'm going to change my Carnot engine with another one, which this time works between the temperature of T1 plus dT1 and T2 plus dT2. And run this over and over again till both of these guys reach a final temperature which is equal for them. Let's say it's TF. So from conservation of energy, I can write that dq1 is equal to dq2 plus dw. Also, I can write that dq2 is equal to, C2 times dT2. Let's say the lowercase t is the temperature of our system at some point in the middle of the process, and capital T1 and T2 are the initial temperatures. And I can write that dq1 is minus C1 dt1. The minus sign is because of that. If dq1 is positive, then the change of the temperature of the first object should be negative. So here should be a negative sign. Now I can write this equation as dq1 minus C1 dt1 is equal to dq2, which is C2 dt2 plus dw, and I can rewrite this as C1 times dt1 plus C2 times dt2, let's move this a little bit, is equal to, plus dw is equal to 0. Now, using the efficiency that we know the Carnot engine has, eta is equal to 1 minus T2 or T1. This is equal to dw over dq1. So I can write dw as dq1 times 1 minus T2 over T1. And I can write dq1 as minus C1 dt1. So dw would be minus C1 dt1 times 1 minus T2 over T1. Now, if I put dw into this equation, into this one, I can write that C1 dt1 plus dw, which is minus C1 dt1 plus C1 times T2 over T1 times dt1 plus C2 times dt2 is equal to 0. So these two terms cancel out, and if I divide both sides of this equation by a factor of T2, what I would get is that C1 dt1 over T1 plus C2 times dt2 over T2 is equal to 0. This is a real famous differential equation, and we can write that T1 to the power of C1 times T2 to the power of C2 should be a constant. And we all know that at first this is equal to T1 to the power of C1 times T2 to the power of C2. This is a little bit messed up. And at the final state, T1 and T2 both are equal to TF. So TF to the power of C1 times TF to the power of C2, which is equal to TF to the power of C1 plus C2. And from that I can write that TF, the final temperature which these objects will reach, is equal to T1 to the power of C1 over C1 plus C2 times T2 to the power of C2 over C1 plus C2. Now I can use the conservation of energy for the whole process and write that Wm, maximum work we can get out of the system, is equal to the amount of energy which we've extracted from the first one plus the amount of energy we've extracted from the second one, which is C1 times T1 minus TF plus C2 times T2 minus TF, and that's it. You can plug in TF into this, and it won't give you a simpler one, equation. Basically, I prefer to keep it this way. Yeah, that's it. This is the maximum amount of work you can get out of a system of two objects, which one has a higher temperature than the other one. This one doesn't have anything special, this equation, but this one, it has a special kind of symmetry. It's beautiful. It's real nice, and I thought it would be nice to share it with you guys. Yeah, that's it. I hope you guys enjoyed it, and see you later.